Okay.
If I find out I have coronavirus, I'm not telling anyone, and I'm just gonna touch as many people as possible.
We're gonna get started. So yeah, a couple of you already heard me say this, but we're just gonna do English practice and then math notes and a little bit of practice today. So we have a little less than 2 hours, which is fine. But I don't really care what we do first. It's kind of up to you guys.
Math.
Math. Yeah.
English.
Oh, yeah. General consensus. Okay, so yeah, I haven't done math with you guys, but basically what we're gonna do is go through some pages in here. I'm just gonna write some notes up on the board, kind of explain everything, let you guys ask me questions, and then I'll put some problems that cover kind of what we went over, and then give you guys a little bit of time to answer them, and then I'll work through how I would go through them. So yeah, basically all you're gonna need is this packet and then like a notebook and something to write with and a calculator. And if you guys don't have a calculator, I have one. Anyone not bring a calculator? I think it might be low on battery, but it should work. Okay, so we're gonna be going over, pretty much wants us to go over all of these pages, but we're not gonna have time. 1 through 3, 8, and 12. So I'm just gonna start page 1 and then like work through as much as we can get through, and then we'll call it good in about like 15 minutes, just kind of average out the time between the two subjects. So yeah, we're gonna start on page 1. It's basically just like basic geometry, line segments, angles. What math classes are you guys all in right now? You can just like shout it out.
Pre-calc.
Okay, so is pre-calc like the highest, probably?
Yeah.
Here.
No, in
I
this
had an
room.
AP.
Well, in the room, yeah. There's higher classes, but.
Oh, okay, yeah.
I'm taking
So, do we need to go over line segments and angles?
No.
No.
I figured we would probably have a good
trigonometry.
grasp on this. So yeah, just stuff to remember, in straight line, there's gonna be 180 degrees. Complementary angles are basically any two angles that add up to 90, and then supplementary, same concept, but it's any two angles that add up to 180. And again, that's just on your packet. For classes that aren't in as advanced classes in school, basically I would just write this up on the board and explain it to them, but I think we're probably good in that area. So that's page 1. Page 2 is where it gets a little bit more complicated. So I'm gonna write it up on the board and just kind of briefly explain it. It's kind of hard to talk about without writing it up there. Okay, so what we're gonna talk about is basically different angle pairs and relationships that exist between them. Why is this just like not focused? Okay, there we go. Relationships that exist between them and kind of how we can employ those in problems. So the first pair that we're gonna talk about are vertical angles. And those are gonna be equal to each other. Basically, vertical angles are just any two angles across from each other in a set. So it doesn't really involve two separate sets, it's kind of just contained within one set. And again, they're just gonna have the same angle measure. Okay. So another angle pair that we're gonna deal with is what's called corresponding. And they're gonna have the same angle measure again. Basically, it's the concept that 1 through 4 and 5 through 8, these like separate sets, are exactly the same. They're just kind of moved along down this one line, which is called the transverse. You don't technically need to know that, but it's kind of just good terminology to be familiar with. Since these two lines are going to be parallel, and again, that's why we can kind of work with these relationships. If these two lines weren't parallel, they wouldn't really exist in their entirety. Obviously, like, vertical angles would still be, because that's only involving one group, but once you start working between two groups, these two need to be parallel in order to apply those relationships. But yeah, again, concept is that since they're on parallel lines, basically they're the same, you're just moving them to a different position. So corresponding angles are gonna have the same measure, and they're gonna be in the same kind of position, just within a different set. So that'd be like 3 and 7. Make sense? Awesome. Okay, so the next one that it talks about is alternate interior. I'm not gonna write it out, but alt interior. Basically it's gonna be on opposite sides of the transverse line, and it's gonna be sandwiched in between those two parallel lines. And again, they're gonna have equal angle measures. So similarly, still working on opposite sides of the transverse line, this time just outside those parallel lines. It's gonna be what we call alternate exterior. Again, self-explanatory, alternating exterior. Okay, so those are the two kind of like alternate angle pairs. Similar angle pairs exist for consecutive angles. So again, they can exist on the inside or the outside of the parallel lines, and then again, it'll just be interior or exterior. So it's consecutive interior, that would be like 4 and 6 consecutive on the same side of the transverse and within those parallel lines. But this time, instead of being equal to each other, like the alternate interior and exterior ones were, these are gonna add up to 180. Because obviously, just by looking at it, 4 isn't gonna be equal to 6 in their angle measures. So that's consecutive interior, consecutive exterior, same concept, just on the outside of the parallel lines. And again, they're gonna add up to 180. Make sense? Awesome. Okay, so another really important angle pair is what's called adjacent. Adjacent basically just means next to. So it's just gonna be any two angles directly next to each other. And again, they're not gonna be equal, but they're gonna add up to 180. The concept behind this is that they form a straight line, and all straight lines have 180 degrees. So it's pretty evident there, but it would also be like 6 and 8 because it works to form that straight line there. Make sense? So obviously, like if you're given, let's say we're dealing with like alternate interior, and you're given the measure of 6, you could pretty easily know the measure of 3 because they're gonna be equal to each other. You really don't have to do any math involving that. But let's say we're dealing with consecutive interior, where you're given 3 and asked to find 5, then basically you would just use the concept of saying, like, angle measure 3 plus angle measure 5 is equal to 180, plug in angle measure 3, and then subtract to find angle measure 5. Make sense? Awesome. And then for like ACT problems wise, they'll probably throw variables in there as well and ask you to like solve for X or something like that. But again, same concept. Any questions over any of that? Awesome. I really thought that was an eraser. Okay. Okay, so yeah, that's basically it for angles. Then it just talks about quadrilaterals. I'm assuming we all know area, perimeter, basic stuff like that. One thing that I do want to point out So they have a formula right above diagonals, where it says the area is gonna be equal to D1 times D2 divided by 2. And basically, that's just the formula for finding an area of any quadrilateral, so any four-sided shape. But most times, you're gonna be dealing with this concept with kites. Because whenever you're dealing with kites, they're probably not gonna give you the length of like these segments, because you don't really measure kites that way. It's a lot easier and a lot more efficient just to measure them by kind of like their length and their width. But that just turns out to be their diagonals instead of the actual outside measurements, which happens for most other shapes. So yeah, we have D1, D2, basically we multiply those together, divide by 2. So that's what it looks like for kites, but again, like I said, this could involve any quadrilateral. So you could do it for like a rectangle, square, trapezoid, anything really. Make sense? Awesome. Okay, so then it just kind of goes along to talk about properties of diagonals. I'm basically just gonna read through them and explain them. So congruent diagonals, basically that's just gonna be where you have like your D1 and your D2, they're gonna have the same measurement for their length. And that's gonna be with squares, rectangles, and isosceles trapezoids. Isosceles trapezoids are basically like, well, that doesn't look good, like your normal trapezoid, I guess you could say. And these two measurements are gonna have, like they're gonna be the same. And again, then their diagonals are gonna have the same measure. Next one deals with diagonals bisecting each other. So that's squares, rectangles, parallelograms, and rhombuses. So let's say we have a rectangle and our two diagonals. Basically, each diagonal is splitting the other diagonal into two equal parts. So let's say this one's like D1, this is D2. We could say that D1 bisects D2 into two equal parts, and then vice versa, same thing for D1 doing that to D2. Make sense? Okay, so then diagonals bisecting at 90 degrees is gonna be squares, rhombuses, and kites. Obviously doesn't include rectangles, it's pretty obvious that's not gonna be 90 degrees in there. And I would say this is probably gonna be most important for kites. Kind of just like diagonals in general are most important for kites. Most other shapes you won't deal with them too much. So we have our kite. Basically it's just saying that the diagonals, when they intersect, are gonna form 4 90-degree angles. So then, in terms of problems on the ACT, you could do like Pythagorean theorem, trig, within these individual triangles to find either angle measures or like side lengths or something like that. Because there's gonna be a 90-degree angle in there. Something else I wanna point out for kites. Let's say this is D2, this is D1. D2, the longer segment, is going to bisect D1 into two equal parts. They even look pretty similar. But obviously D1 is not gonna bisect D2 into two equal parts. It's pretty easy to see that this is gonna be a lot shorter than that. So again, just some rules to keep in mind. Not exactly like formulas, obviously, but kind of just following that logic through in your problems. You're gonna need it to know the properties to apply, kind of, if that makes sense. So yeah, any questions over that? All good? Awesome. Okay, so that's basically it for page 2. Page 3 kind of just goes through some formulas. Area of a trapezoid, again, not too hard, kind of just something that you have to remember. The way I like to remember it is like the b plus b divided by 2 part. It's basically like you're finding the average of the bases by adding them up and dividing them by 2, and then obviously you have to multiply it by height to give it another dimension. And then kites, the formula of an area of a kite is basically just gonna be what we went over. Yeah. Okay, so then it goes on to triangles. Basically, it just talks about the conditional for a triangle to exist. Sum of two sides must be greater than the third side. Again, not really a formula, but I have seen it sometimes where it'll give you a triangle with like two sides and it'll ask for like the minimum or the maximum of the other side, and it's gonna be dealing with that rule. Where if you take any two sides of a triangle, it's gonna be, and add them together, it's gonna be bigger than the third side, even if the third side is your hypotenuse. The sum of the other two will still be bigger. And then it just kinda goes through equilateral, isosceles, scalene. I'm gonna go through a couple things with that. Okay, so this is gonna be an isosceles triangle. Basically, it's where two angles and their corresponding sides are gonna be equal. So the reason I like to go over this is just to remind people what like corresponding angles and sides means. So let's say we're just looking at this angle right here, and let's call it A. It's gonna correspond with its opposite side, basically the one side of the triangle that isn't touching this angle. So like this side is touching it, this side is touching it, but kind of like its opposite side is not. So if I were to label a triangle, I would label it like that. And there's not really gonna be a numerical relationship between the two. So like, let's say this is 60 degrees. Obviously this length isn't gonna be 60 because you can scale a triangle up and down as much as you want without changing the angle measures. So it's not like a formula or any numerical kind of relationship. It's just more so for like labeling and keeping it straight and knowing which sides are gonna equal which and which angles are gonna equal which. So that's kinda, again, for isosceles, where corresponding angles and sides come into play. So like if we know that this angle is equal to this angle, let's say we know this side is equal to 8, therefore we know that side's gonna be equal to 8 as well. Just because they have corresponding sides and angles like that. Make sense? Awesome. And then just a quick reminder, equilateral triangles, all angles are gonna be the same, all sides are gonna be the same, and for any triangle, the sum of all angles is always gonna add up to 180 degrees. So for an equilateral triangle, 180 divided by 3 is gonna be 60. So no matter how big or small your equilateral triangle is, it's always gonna have 60 degrees for each of its angle measures. Okay, so now we're gonna go over Pythagorean theorem. How many of you guys have dealt with Pythagorean before? I figured. Okay, so that's nice because this will kind of just be a review. So yeah, basically, some mathematician found out that for all right triangles, this rule applies where A and B are gonna serve as your legs. And it really doesn't matter which is which. And then C is gonna be your hypotenuse. Your hypotenuse is gonna be the longest side, and it's also opposite the 90-degree angle. Which makes sense, because within a right triangle, your biggest angle is gonna be 80 degrees. So yeah, I would say just the biggest thing with this, because it's not too hard, it's typically just straight substitution and then solving for one of those other variables. Just make sure that, like I said before, it doesn't matter which one is A and B, but C is always gonna be your hypotenuse. So where I see some people mess up is, let's say we have something like this, where we're given C, and let's just call that B. They would say this instead, just because it's kind of more convenient to solve it like that, or they just like kind of slip up and don't really think it through. But obviously, we would have to plug it in like this, because our C is going to be equal to 4. Make sense? Any questions over Pythagorean? Or triangles in general? Sweet. Okay, so that's basically it for pages 1 through 3. So now we are going to go through some problems with that.
Jesus.
Okay, so I'm basically just gonna write like 2 or 3 problems up on the board. You guys can start as soon as I start writing up there, and then we'll take like 4-ish minutes, 5 minutes, kinda just depends upon like how it seems like you guys are doing, and then we'll go over them, and I'll show you guys how I worked through them.
Someone just sneeze over there. Oh, God. Oh, I know how to do this one.
He's at.
Can everyone see that? Alright.
Yeah.
Okay, awesome.
Bless you.
Are we good to go over answers?
For sure.
Wonderful. Okay, so this first one is basically what we're talking about with like intersections of lines and relationship angles and pairs and stuff like that. So it says that M and N are parallel and it wants us to find X. So basically what I'm gonna do is I'm gonna focus on the triangle that those three lines form there, because I know that if I find this angle here, I'll automatically know X due to vertical angles. So I'm just gonna kind of blow that up just so it's easier to see. And again, that's what we're solving for. So using the law, whatever relationship of corresponding angles, if I have two parallel lines and a transverse line intersecting them, and it forms those two groups, I know that this angle here is gonna be equal to this angle here. So I'm gonna say that this is 65 within that triangle. Make sense? So then I'm basically gonna do the same thing here, except now we kinda just have to go through one more step. Again, that's just the law of corresponding angles. Instead of finding out this, obviously we found its adjacent angle, so I know that since these two angles form a straight line, they're gonna add up to 180. So if this angle is 100, this angle is gonna have to be 80, because 100 plus 80 is 180. So then I know this angle is gonna be 80. Make sense? Awesome. So now I know that within a triangle, all three of their angles are gonna add up to 180. So that's basically what I'm gonna do. I'm just gonna refer to this as X. So we have X plus 65 plus 80 is equal to 180. So we have X plus, what is that, 145?
Bodie.
Okay, done.
Yep.
So then we just get X is equal to 35 degrees. Make sense? All on board? Wonderful. Okay, so this one is something that the ACT is gonna do a lot, where they give you a word problem about a figure, but they don't actually give you the figure. So basically it's just dealing with a ladder reaching up a wall, and it wants to kind of know like the bottom measurement. So whenever there's a problem like this, I always just draw it out. It's kind of like common protocol. It really just helps you like visualize it better and figure out what you need to do with the information and the numbers that you're given. So it says that the ladder is 10 foot long, so that's like my actual ladder. This is my wall, and it says it reaches 8 foot up that wall, and it wants to know the distance from the base of the ladder to the base of the wall. So basically we're just gonna do Pythagorean theorem, plug in what we know, find out what we wanna know. So we have a squared plus b squared is equal to c squared. My c is gonna be equal to 10, I'm gonna say my b is equal to 8, and then you can leave it as a, or you can just put it as x, I prefer x, but it's up to you. So then we have x squared plus 64 is equal to 100, subtract 64 over, we get x squared is equal to 36, take the square root of that, and yeah, it's in feet. X is gonna be equal to 6 feet. Make sense? Any questions? Awesome. Okay, so then this one basically gives us a trapezoid with the triangle portions of it, I guess you could call it, shaded, and it wants us to find the area of the shaded region. So there's a couple ways to go about this. One that takes a little bit longer is you could find the area of the entire trapezoid, and then the area of the rectangle, subtract the area of the rectangle from the trapezoid, that'll get you your shaded area. Or, that was like the one that I did first, but then I was teaching a class, and someone's like, oh, can you just do this? And I was like, yeah, it makes a lot more sense and it's a lot quicker. So, basically, we know that this is gonna be 4 right here. And we know that this entire thing is gonna be equal to 8. So I know that added together, basically, these two are gonna equal 4, because a minus 4 is 4. And I know that this length is gonna be 3. So essentially, kind of like the reasoning behind it is you really won't change the dimensions at all, if you, I'm just gonna kinda like redraw it, but if you like push this side in and push that side out, keeping that rectangle in there. It's basically gonna do the same thing. So then you would have, like, the 4 up there is gonna stay the same, then it'll be 4 down here and 4 down there. That's basically what you're doing, or it's kinda like you're just taking that triangle off and like flipping it to that side. So then, by that reasoning, oops, this is gonna be our new shaded region, so then we just do the area of a triangle, which is 1/2 base times height. 1/2, 3 times 4 is gonna get us 6, whatever it is, units squared. Make sense? Awesome. So again, you could do it the other way, that's probably like the more technical way, but ACT is all about finding like little shortcuts that you can use, just so you don't waste your time on stuff that's not necessary, so. Any questions over those 3 problems? All good? Wonderful. Okay, so you have like 20-ish more minutes, so we'll keep going with math. And now we're gonna be working out of page 8, which is basically just quadratic equations. Okay, so, I'm assuming you all have worked at least a little bit with parabolas? Yeah, awesome. Okay, so, I'm gonna go like a little bit more in depth with quadratic equations than I did for lines, just because it's a little more advanced, and the SAT, or not the SAT, the ACT is gonna test a little bit more heavily over it. Okay, so this is gonna be our basic equation for a parabola. And yeah, it's kind of comparable to slope-intercept in the form that like, obviously it's just a basic, formula for it. But with slope-intercept, it's really convenient because you really don't have to do any manipulation with it in order to find out 2 really important things about your line: the slope and the y-intercept. From there, you can basically just graph it really without thinking. Quadratic equations are a little different just because they're a little bit more complex. So like, there's not gonna be a single slope throughout just because it's a curved line. Did you say some of you guys are in pre-calc?
Yeah.
Have you, actually no, you probably haven't done like slopes of curved lines. Yeah, no, that's more calc. But that like basically is literally all of calc, just derivatives and integrals, but do not worry about that at all for now. But basically it just says that on a curved line, the slope is gonna change. So we don't have one number where we can look and say, okay, yeah, that's our slope, but we don't really need to for parabolas at least. So you can use this equation to manipulate it, and then you can find out some things. It just takes a couple more steps, but it's still really important to keep this in mind. And obviously A, B, and C are just gonna be different coefficients. So what we're gonna do is we're gonna look at each of those coefficients individually and then break down what that can tell us. Okay, so first we're gonna look at A, and depending on the sign of A, it's gonna tell us whether the parabola is gonna point up or point down, or open up or open down. And then from there, we can figure out if we have an absolute minimum, if our A is gonna be positive, or an absolute maximum if our A is gonna be negative, which seems kind of contradictory, like having a positive and having it be a minimum, having a negative and having it be a maximum, but again, that's kind of just the nature of the graph. And both your minimum and your maximum values is just gonna be your vertex. Make sense? Awesome. Okay, so then that's just dealing with the sign of A, but the actual value of A is also gonna tell us about its slope. So if our slope is greater than, or not if our slope, if our A is greater than 1, it's gonna be stretched vertically. So it's basically like you're taking the very top and the very bottom and stretching it vertically. So that's if A is gonna be greater than 1. If A is between 0 and 1, so basically if A is a fraction, then it's gonna be compressed vertically. So it's like you work from the top and the bottom, and you're squishing it down vertically. So basically that would be like a steeper slope, and that would be a more gradual slope. Make sense? Awesome. Okay, so that's A. C, kind of convenient, is basically gonna be our y-intercept, where if we plug in 0 for x, we're gonna get whatever C turns out to be. So at least from there you can kind of get like a concept of where your graph is positioned, hopefully. So something else that's really helpful is to find out the axis of symmetry of your graph. So basically, the axis of symmetry is just a certain point on the x-axis where if you were to draw an imaginary line and fold your graph along that imaginary line, it would be symmetrical on both sides. So that's kind of where like manipulation of the coefficients come into play. Instead of just having one value, like let's say B, and being like, okay, yeah, that's the axis of symmetry, we just have to manipulate it a little bit. So our x value is gonna be negative B divided by 2A. And that's also gonna be the x value for our vertex. So let's say it wanted us to find the vertex of a graph. Basically, in order to do that, we would find the axis of symmetry, that would be our x value. And then once we have that x value, we would plug it into our function and then solve for our y value. And then put the two together in a coordinate pair, that's gonna be your vertex. Make sense? Awesome. Okay. Now we're gonna talk about discriminants a little bit. He kind of emphasizes it on this page. I'm not gonna go too in depth just because quite honestly they don't deal with discriminants in and of themselves on the ACT a lot, at least from my personal experience, so I just don't wanna waste our time going through it. Basically, it's just looking at the quadratic equation of x is equal to negative b plus or minus square root of b squared minus 4ac, 4ac all over 2a. What the discriminant of a quadratic equation is looking at is basically everything under the radical, and whether it's greater than 0, equal to 0, or less than 0. So if it's greater than 0, then it's gonna be some like real number in here, right? Because we can take, even if it's not a whole number, we can take the square root of any positive number. So let's say it's 4, then we'll have like plus or minus 4, so that's gonna give us two different values for where our graph crosses the x-axis. If it's equal to 0, then square root of 0 is 0. Basically, you're not really gonna think about it in terms of like plus or minus 0 because that doesn't do anything. So you're really only gonna have negative b over 2a, it's only gonna touch in one spot, and it just happens to be that that one spot is the vertex, which makes sense, because if you take away this whole part, you're just left with negative b over 2a, which we just learned was our axis of symmetry. So if it touches at only one spot, it's basically just gonna touch at the vertex. And then let's say b squared minus 4ac is greater, or not greater, is less than 0. We know we can't take the negative number, or we can't take the square root of a negative number, right? So basically it's not gonna cross the x-axis anywhere, it's kinda just gonna float up or it float down. So it's not gonna have any real like roots, solutions, zeros, all those terms, all are basically just asking where does it come in contact with the x-axis. Make sense? Awesome. Okay, so yeah, then it just talks about minimums, maximums, axis of symmetry, but we already went over all of that. Something else to keep in mind for parabolas. I kinda just mentioned it, but it's obviously really important. So, like I said, the roots or solutions or zeros of a parabola are basically where it crosses the x-axis. Like I said before, there could either be no answer, one answer, or two answers. And that's kind of just the concept of taking whatever they give you in this form and putting it into something that looks like this. Obviously, I'm not, there's no, well, I guess there is like a concrete way to write it. But it kind of just depends on the numbers that you're given. So that's when you're gonna factor out and then set it equal to 0. Because again, if this is our y, we're looking for where it crosses the x-axis or where y is equal to 0. So then from there, depending on whatever you put in here, you're gonna set each one individually equal to 0 and solve for x, and that'll tell you where your graph crosses the x-axis. Make sense? Any questions over that at all? Awesome. Okay, so now we're gonna go over some problems for quadratic equations. Okay, we're good to go over answers?
Yeah.
Awesome. Okay, so for this first one, it's basically just asking you to factor it out and then set it equal to 0, and then set each individual part equal to 0, and solve for x. So, obviously when we start, we just start with 2 sets of parentheses. And then depending on whether or not we have a coefficient out here, that's kind of what I deal with first. So, it's kind of nice we don't have a coefficient out there, so we're just gonna put x for both of our terms. Or it's technically like 1x for each. Let's say it was like 2x out there, then one of those would be 2x, the other would just be x. Or if it's 4x, then you have to kind of do trial and error with how you're gonna kind of factor that out. But no coefficient, so we don't have to worry about it. So the next thing that I like to focus on is my sign, like whether it's gonna be plus or minus within those 2 parentheses. And you can basically just tell that from looking at these 2. So 24 is gonna be kind of like our product of our 2 terms. So if you have 2 terms being multiplied by each other and the answer is a negative, we know we're gonna need one negative and one positive. So since there's no coefficient out front, we really don't have to worry about where we put the plus and minus within those 2 parentheses, because they're the same set, So from now, I basically just like to look at what my factors are gonna be, and possibilities for those. So since we're dealing with 24, we could have 1 and 24, 2 and 12, 3 and 8, or 4 and 6. And since one is gonna be positive, one is gonna be negative, I'm basically just gonna look at the difference between those 2 factors for what one to choose. So, pretty obvious to notice that the difference between 4 and 6 is 2, which is my middle coefficient, so I'm gonna go ahead and choose those. So, now I know my 2 factors. Basically, the next step is just where to put them within those 2 parentheses. So, since it's a negative attached to our 2, I know that the bigger number is gonna have to be associated with a negative. So, 6 is obviously bigger than 4. So that's gonna be our 2 sets of parentheses. Any questions over that? Awesome. So then basically we just set each set equal to 0. And solve for x. So our solutions or roots or zeros, wherever you wanna call it, is gonna be x is equal to -4 and x is equal to 6. Make sense? Any questions? Awesome. Okay, so that's dealing with where it crosses the x-axis. This is dealing with the vertex. So we're just giving it in our basic form, which is kinda nice because we don't have to multiply anything out. So in order to find the vertex, I kinda already went through this. Okay, but basically, in order to find the vertex, we're gonna focus on our x coordinate first. So to find that, we're gonna use the equation x is equal to -b over 2a, where we have our coefficients out in front of our variables, or just by themselves. So then from here, I'm basically just gonna plug it in according to what I'm given. So my b is gonna be -5, and my a is technically just gonna be 1. Double negative on top cancels out, and the x value for my vertex is gonna be 5 over 2. Make sense? So then from there, kinda like I said before, I'm basically just gonna plug that into my function. So then, if I were you guys, I would probably just like type this string out in my calculator. Just make sure you're careful with parentheses. And then, I believe it comes out to -1/4. So we have our x component, our y component. When we combine them in a coordinate pair, that's gonna be our vertex. Make sense? Awesome. Any questions over anything with Bradlow's quadratic equations? All good? Awesome. So, perfect. We are going to take like a 5-minute break, and then we'll come back and do some English.